to similar sort of way of thinking, scaling behavior, scaling laws, etc. But the subject is really very different and has been a source of confusion, I think, for many years. So let me start by introducing the subject. So what are glasses? I mean, what is the basic glass phenomenology? So you probably all know that liquids exist at high temperature. So here is a typical phase diagram. This is the specific volume in a fluid or in what will immediately become also a solid. So this is the specific volume per molecule. This is the temperature. And the phase diagram is such that at high temperatures there exists a liquid. And when we reduce the temperature, the specific volume reduces. Usually, we're not talking about water where there is a bump, the anomaly of water. A generic liquid sort of continues in this way. And then there is a melting temperature, Tm. And if you go slowly and you cool, such a liquid will generically crystallize and crystallize into a solid that has a crystalline order, which is a repetitive periodic order. We're not talking about the new Nobel Prize of Dani Shekhman showed us that there is also quasi-periodicity. In usual crystals, you have a periodic orbit, a periodic order, and
Sorry.
You double as a door.
Anybody else? Okay. So periodic order. However, if you don't go slowly at this point here, and you quench rapidly through the melting temperature, you enter a regime that is known as super cold liquid. So that's generic. That's in many liquids, including water, by the way. You can cool such that the system still is a liquid, but what happens is that this liquid becomes more and more viscous as you go down, and in fact quite rapidly so. And at some point, it becomes so viscous that it is acting as a solid on at least short time scales. Now, what is the basic difference between a liquid and a solid? Obvious. A liquid, any strain that you put on the outside, it flows. A solid, on the other hand, you put a strain and it reacts elastically. So this is where you get, and you call the material that happens a glass, and the glass is different from the crystal, even though the slope of the specific volume versus temperature becomes similar to the crystalline solid. Nevertheless, this is an amorphous solid. It doesn't have the periodicity that is typical to the liquid. And in fact, if you look at standard correlation function like G2, the second order correlation function, it's indistinguishable in the glass and in the liquid. So it's a disordered material, amorphous, but it acts as a solid from the point of view of the mechanics. I'll show you in a minute that this in fact has a marvelous mechanical properties, very different from the crystalline. And this is called the glass transition, where you go from a supercooled liquid to something that behaves like a solid. But I want to immediately stress that the glass transition is an ill-defined concept in the sense that it depends on the protocol, on the speed of cooling, and all kinds of things. So this can happen at different temperatures, and you get sort of structures that are more or less dense depending on the speed at which you quench. So the glass transition is somewhat ill-defined.
Somebody else coming in.
Maybe it'll be safer for everybody. So here is what happens in terms of the measured viscosity. It's a typical plot. So you have the logarithm of the viscosity in units in poise, and this is the famous plots that people do in experiments, and they write it as Tg over T, where Tg is artificially defined as the point at which the material has a viscosity of 10 to the 13 poise. I don't know why precisely that's thing, but that is already traditional. 10 to the 13 poise is about the viscosity for which it takes a day for the material to flow out of a beaker. Okay, so that is sort of an arbitrary definition, but nevertheless, the point that I want to stress is that the viscosity shoots up very rapidly as you go down. It can go up, say, 14 orders of magnitude or 13 orders of magnitude when you go down. There are two possible scenarios. This is, for example, for silica, where this is straight. For other other materials, it is a curving thing, and these are known as fragile glasses, these are known as strong glasses. These are all technicalities that we don't have to get to. There have been a lot of arguments whether this continues to diverge forever, or is it going to go to infinity at a finite temperature. I believe now strongly that there is no infinity at any temperature between, before zero temperature where the thing goes to infinity. But again, this is not what I want to stress today. So what I really want to discuss today with you are typical stress, strain, and energy strain curves in such systems. And what we're going to start is with systems that are very simple, that is, they are at zero temperature, and we're going to strain them in a quasi-static fashion. And what you do, here are examples of numerical simulations in which you can take a material, indeed prepare it at high temperature as a liquid, then quench it into a low temperature, make it into what we call now a solid, an amorphous solid. And now you can strain it by taking all the positions of the particles and changing, for example, this is in 2D, the x coordinates, the xi prime go to xi plus some delta gamma yi, and all the yi unchanging, so this is really a shear strain. You push like this, and what you can measure, for example, the stress in the material or the energy in the material. So this is the stress. The stress are just the force that the material is now putting back on as a result of the strain. And typically what you see is there is a region here which is sort of linear. This is the, as I said before, this is the typical thing for a solid that reacts elastically, and the slope here is known as the shear modulus. In fact, when you blow up, you see there are little drops also here that I may discuss or may not discuss in the sequel. But at some point, there is what we call the yielding transition, where the stress cannot cross a given mean value. And you see it goes up and then falls, up and falls, up linearly, falls abruptly, up linearly, falls abruptly, etc. This is how the stress behaves. The potential energy actually goes quadratically up and then falls, and then there are quadratic little ranges here and drops, etc. So what are these drops? These drops are defined or are known as plastic responders. So when the system stops behaving elastically and there is an abrupt change, we call this plasticity. And at this point, the system becomes a very complicated fluid in some sense. It begins to flow, but it flows in a stop-and-go fashion in the sense that there are sort of linear regions where the stress grows, and boom, it falls down. Now, why we have a linear behavior for the stress and quadratic for the energy? It's very simple. So as I said, linearly, for linear theory, the stress is proportional to the strain. So the strain is here, and as I said, the coefficient of proportionality is known as the shear modulus. The energy, potential energy, is the product of the stress and the strain. And of course, the energy is extensive, so there is the volume here, the stress is intensive. Now sigma gamma, when you have a linear behavior, sigma is mu gamma, goes like gamma squared, and therefore these are the parabolic stretches when the system reacts elastically.
What's the statistics of these jumps?
That's the next question.
Okay. And this is simulations?
These are numerical simulations, but you see this also in experiments, especially in colloids, in bubble rafts, things like this that behave similarly. As I'll argue in a minute, the size of these drops depend very sensitively on the system size. So we'll see how it affects the system size and the statistics of these things.
But is Leonard jonesing them, or is it, are the MPs?
Whatever. I mean, we've now run a huge variety of things, Leonard Jones type, but also in metallic glasses, which is a material I'm going to describe momentarily, which is not a binary potential thing. It has, in fact, electron gas and connects every particle to every particle. It's very similar. in the way that it appears to the eye as a stress versus strain, or energy versus strain curves. Now, what is plasticity? So plasticity has been studied very carefully at the sort of last decades of the 20th century for crystals. And for crystals, it's understood almost entirely. Let's say crystalline material, when they're in the bulk, cannot be perfectly periodic. Entropy raises its ugly head, and you have dislocations, defects, etc. Now, dislocations have the property that when you strain the material, they glide, they move. And that glide is an irreversible process, and this is why energy is lost, strain falls down, and the glide of dislocations is the source of plasticity in a crystalline solid. When we started, in the last 30 years or so, people have started to study these amorphous solids, and the phenomenon of plasticity has not been understood in a very convincing way. And I want to stress here that this is one of the things we want to point out today, that I believe we now understand very clearly what are these plastic events that we see here, and this is sort of a novelty in the last 2-3 years that I want to explain. People tried to approach plasticity in amorphous solids in a way that was a continuity of the thinking for crystalline solids, in the sense that they tried to say, aha, there are special regions in the material that are more sensitive to emissions to the strain than others, and these are known as shear transformation zones. It's a notion that started to be discussed by Ali Aragon in MIT, but in more recent years, Jim Langer has tried to develop a theory on the basis of the existence, pre-existence of special regions, weaker regions or weaker spots in the material that yield in an easier fashion than others, and I want to argue to you this is not a very useful way of thinking, and I'm going to explain what I believe is a good way of thinking. For some reason, the thing that I've jumped on one slide that I think is interesting, I mean, this is it. So what I want to actually show you here is how amorphous solids react in a mechanical way differently from crystalline solids. So what I'm going to show you now is a film of an experiment that was done by, in fact, by a company that now produces metallic glasses. And what you're going to see are 3 tubes. And the tubes are such, there is a stainless steel at the bottom here, there is titanium here, and there is what they call liquid metal, which is a metallic glass, which is a glass made from a combination of few metals, melted, cooled down in the usual way. And now we throw a steel ball from the same height. It reached this height over the stainless steel, that height over the titanium. It went out of the box over the metallic glass, and now we throw again the ball from the same height, and you see that on the steel it is already finished, on the titanium is going to finish in a short while, on the metallic glass it jumps again and again and again and again and again, and in fact the restitution coefficient of the metallic glass is so much higher than the restitution coefficient of the stainless steel on the titanium, and that's because there are no little things that move. Let's say in the crystalline material we have all these dislocations, they move, they take out the energy from the falling ball. In fact here, the main reason for the attenuation of the jumping of the ball is the air friction. And the restitution coefficient here is about 0.99 compared to by 0.6 or so on the stainless steel and about 0.8 on the titanium. This is why also these materials are becoming very interesting from the point of view of technology. I can say also in a way, just in passing, that the golf club of Tiger Woods is now made of this metallic glass. You see another couple of meters.
But he's not doing so well now.
Well, his personal problems are besides this talk, okay, in a different talk.
So these are so-called bulk metallic glasses as opposed to the ribbons.
Okay, so you may or may not know that to make a metallic glass is not easy. In the sense you have to cool extremely rapidly. So what has been done in the past, say even 40 years now, people have splashed molten metals on a very cold substrate to get the ribbons or, you know, a very two-dimensional kind of metallic glasses. For reasons I'm going to explain next, it's very important to make also bulk metallic glasses. So the way that this has been achieved, mainly in the laboratory of Bill Johnson in Caltech, is to mix a few metals together, like 4 or 5 metals. Then they are confused what kind of crystal tool to make, because usually metals are very prone to crystallization. And then they don't have to cool so fast, and then they begin to be able to make bulk metallic glasses, not just ribbons. Bulk metallic glasses are going to be exceedingly important for technology for the simple reason that, like the restitution coefficient mechanically, they're also very soft magnetically, in the sense that you can switch a magnetic field almost without any cost of energy. Now, where do you switch a magnetic field 60 times per second? In transformers. And in transformers, usually the core is made of a crystal metal, and the same story of the dislocations moving is taking about 30% of the energy out. So if you can make transformers with metallic glass and save 30%, you know, these are billions and billions and billions of dollars. So this technology is now building up. There is one startup company already in Israel, and I'm also told that the Westinghouse is also trying to do bulk metallic glasses for transformers. So these things are really interesting technologically, but this is not what I'm going to discuss with you today. I want to show you now a film of typical simulations, just to show how plasticity here is not uniform, complicated, and stuff, but let me show you how it works. So this film is going to show every particle that has changed its local neighbors is going to paint. Okay, so I'm going to put a red color at the beginning on every particle that has changed its local neighbors, which is a plastic event. In elasticity, you only strain the particles with respect to each other, but the neighbor list is not changing. Here, the neighbor list is going to change. And so you see, while you strain, you begin to see all these red regions, but then the plasticity becomes more intense and more localized, in the sense that everything now occurs here and here, and you see that it's not a homogeneous thing, and it's a complicated process, and yet we want to begin to understand how to talk about it and how to specify what is going on. So, statistics, Moins, this is for you. The obvious question. So we can measure now, in a steady state, the average, say, delta sigma. So delta sigma would mean here that I'm going to look at every point where I drop and measure the stress drop from the point that it started to the point that it ends. And that will be a delta sigma, and now I can average over a long stretch. And the same thing I'm going to do with energy. And what I'm going to ask is, how does this depend on the system size? So n is the number of particles in my system. And you see that there are pretty good scaling laws. Delta U appears to go like n to exponent alpha, and delta sigma like n to exponent beta, except that one is positive and one is negative. Alpha is of the order of a third, and beta is of the order of minus 2/3. And I'm going to argue to you soon that these are actually exact numbers, that alpha is a third and beta is 2/3, and without dots, that these are actually rational numbers, a la Pythagoras. And it's very easy to make one relationship between the two. Let's say by conservation of energy, you realize that if you're now going over a stretch where the mean strain is constant, so we said we're going to see something like this. So here the mean strain is going to be called sigma y. So sigma y times delta gamma. I told you that sigma y times gamma times v is the energy. So the stress times the strain made extensive is the energy. And therefore, on the average, you must have that the average strain times the average size of the distance in gamma here is the average energy drop, and therefore this immediately will give you a scaling law, because delta gamma, because of the linearity, delta sigma goes like mu delta gamma, so delta gamma has an n to the beta, v has n to the 1, delta u has n to the alpha, and therefore the scaling law that you get is that alpha minus beta equals 1. And you see that these numbers, of course, agree, but I'm going to argue to you these numbers are exact.
Was that the simulation of these ones? Or
These are from numerical simulations.
2D?
What?
2D?
2D, and in fact, the first clue that these numbers should be simple to understand was the three-dimensional simulation gave exactly the same numbers. And coming back to your question from the morning, we use that when these numbers are rich, then they have to be very strongly d-dependent. When you find that they are not d-dependent, you know that the answer must be close to the surface. And I'll show that it's very close to the surface. By the way, you don't need to look only at the mean drops or the mean changes. You can look also at the stress fluctuations. So delta sigma squared is nothing but sigma minus sigma yield squared, again on the average. And you see that this object also scales, and it scales with a number that is surprising. In what sense? Sigma is an intensive variable. For intensive variables, usually you expect that the fluctuations are going to go down like 1 over n for any normal intensive variable. In fact, the answer here is that it goes like n to the 2 theta, where theta is of the order of minus 0.4, so we have n to the minus 0.8, very different from n to the minus 1, and very clearly different from that, showing that this is a very interesting process that is not trivial, and the fluctuations have some rich correlations that need to be understood. Okay, now the next question that I want to discuss is what is plasticity? And for that reason, I want to switch to here, where I have a wonderful thing that was done by my student Idan Lerner, that explains really what is going on in the plastic deformation. So what is plasticity? As I said, we have a strain, an outside strain. The outside strain is responsible for changing the positions of the particle in what we call an affine way. So every xi goes to xi plus delta gamma yi, etc. And yi goes to itself, zi goes to itself in a three-dimensional straining. But what I want to argue is in a amorphous solid, there is an additional response which we call non-affine, this ui. And I want to make a little movie here because this is the essence of what is happening. So here is an example of a little system that I'm going to strain. When I strain it, you see I have an arrow that is longer here and is shorter here. This is a shear strain. So this is what I'm going to do from the outside. As a result, the system will move. Okay, so that's the strain step. Once you strained, you see in a crystalline solid, it will be still in equilibrium because you strain all the bonds, but there's no reason for an additional change. What happens in an amorphous solid is that now you create forces when you did it. And all these forces are rather random and are showing in different places, and this is typical to an amorphous solid. This is not going to occur in a crystalline solid. And now, if you want the system to be in a mechanical equilibrium, you have to allow it to do another non-affine change, which is this. You see, whoop, there is a rearrangement, and this rearrangement is the non-affine part of the response, which is crucial. It's crucial and it's typical to amorphous solids. And this is going to be the source of understanding of what is the plasticity. Why? Because now I'm saying, okay, I've done these two steps, so the forces on all the particles were zero before and are zero also after the non-affine step. So d fi d gamma, fi is the force on every particle, gamma is the strain, is zero. But on the other hand, what is fi? Fi is nothing but the force on the particle. Hello, Christopher. So a force on the particle is minus the energy, the position, du dri. That's the force. So d gamma of du dri has to be zero. Now, since xi and ui are related linearly, when I do du dri, du dy is the same, so I have this equation to consider. Now this equation has a second derivative, as you see, one full and one partial. So now let us interpret this. This equation says, okay, I have to take the second partial derivative, d squared u d gamma dy, but I have also another contribution for the fact that ui depends on gamma. You saw that this non-affine thing depended on how much I strained. So I have now another contribution, which is due to the chain rule, d squared u dy duj, and multiplied by duj d gamma. Okay, so what are these objects? These objects are actually well known. D squared u dy duj is nothing but the so-called Hessian matrix for this material. So we have here hij, duj, d gamma. This object is a vector. It has only one index here, so I'm going to call it psi I, and it is known as a non-affine force. And you see, when I'm going to now invert for duj d gamma, I want to know how much I'm getting of this non-affine thing. I'm going to have the psi on the other hand, on the other side, and there's going to be an h to the minus 1, and Hessian to the minus 1. And whenever you invert a matrix, there are of course dangers, because this is how it's going to happen. You see, when you strain a system, these are the low eigenvalues as an example of this Hessian matrix. At equilibrium, they are distinct and there is no problem. Now you begin to strain, and what you find is that one of the eigenvalues dives to 0. Okay? And then h to the minus 1 is going to the value. This is plasticity. This is what the plastic event is. It's an instability. And in fact, it's a very simple instability. It's a saddle node bifurcation. And as typical to saddle node bifurcation, the eigenvalue, the lowest eigenvalue we're going to call lambda p, goes to 0 as a square root, gamma p minus gamma. And this, I'll show you, determines the exponents that I just discussed. And that is the generic thing. Now, what is the eigenfunction? Well, the eigenfunction is looking like this. The eigenfunction, surprisingly, is very localized. And why do I say surprisingly? See, we have here amorphous solids. Now, you know very well that in disordered systems, there is the phenomenon of localization. But localization in amorphous systems in equilibrium always happens with high eigenvalues. That is to say, if you look at the spectrum of an amorphous system, usually the low eigenvalues are always associated with the delocalized eigenfunctions. High eigenvalues, high energy, become localized. What happens here is the same thing. When we are at equilibrium, the eigenfunction that is associated with this fellow is extended. And there's no way that you can guess where it's going to localize. There is no STZ. There's no shear transformation zone. When you look at the start of the experiment and you try to say where the plastic event is going to be, I challenge you. There's no way that you can do it. However, when the system is strained, the eigenvalue goes to 0 and a low eigenvalue becomes associated with a localized eigenfunction. And what is this eigenfunction? It's simply what we call T1 process or Bachner move in mathematics, etc. These are particles, you see the arrows, part are going out, part are going in. It's a quadrupole event, and that is the plastic event that is taking place. So the eigenfunction that is associated with eigenvalue goes to 0 is plasticity. And that is the same when you are in equilibrium, where you are in the steady state. You have these quadrupolar events that are actually the way that the plasticity is showing itself. Now we can go back to the first thing here. Okay. And indeed this I already explained. So that's this story, and now let us understand therefore that we have eigenvalues that go to 0 as a power law, square root in gamma p minus gamma, and I want to argue to you that this determines the exponents that I showed you before. So let's start by understanding what is the way that the energy barriers are going to 0. So I claim that the system, in fact, in an abstract way, is sitting in sort of energy landscape. And when you strain, there is a saddle node bifurcation in the sense that one region like this becomes sort of goes through a saddle node bifurcation. In fact, the minimum and the maximum collide at the saddle. And what I want to do, I want to estimate how this energy barrier that separates the minimum and the maximum goes to zero when gamma goes to a gamma p. So what I'm going to do, I'm going now to take the coordinates and find a new reaction coordinates. So I'm going to call the position of the particles xi, the position at the minimum, xim. So I start with the position at some minimum, always in equilibrium, okay, where the Hessian is stable, etc. And now I'm going to add direction coordinates in the direction of the eigenfunction that is going to become localized. So this is the plastic eigenfunction. S tilde is going to be the direction coordinate, going towards that thing. When I do this, I can now expand my energy. This has to be S tilde. I apologize, the same S tilde is here and here. So the energy as a function of S tilde is the energy at the minimum. First derivative, of course, is zero because I'm at the minimum. Second derivative gives me the Hessian, and therefore on psi p is going to give me the eigenvalue lambda p. And third, the derivative is sort of boring, with the coefficient being the third order d cubed u ds cubed that you can write in terms of the eigenfunction, but the point is that it's not singular. So I have the energy, and now what I can do, I can find the two extrema of this thing, find the minimum and the saddle, and I find the position of the saddle by taking the first derivative and equating it with zero. So I have, of course, the x minimum as one solution, and the other solution is the saddle. And when I do this, I find that it looks like x minimum minus 2 lambda p over Tp times the eigenfunction. As I said, Tp is not singular. Okay, so now I know the energy at the minimum. I know I can now put it in back. I find the energy at the saddle, I know the energy at the minimum, and the difference between them is written explicitly as 2 lambda p cubed over 3 Tp squared. As I say, this is non-singular. Lambda p, we said, goes like a square root to 0, as gamma p minus gamma to the half, and therefore the typical energy barrier goes like gamma p minus gamma to the 3 halves. Okay? So that is simply a consequence of the saddle node bifurcation. Here is an example of the numerics. You can check this. So these are for systems of different sizes, and you see the delta E as a function of gamma p minus gamma. You can just follow this numerically, and you see that the scaling law is obeyed in a very, very convincing way, which of course no surprise, it's a very simple argument. Okay, next. So remember this, we have delta E goes like delta gamma to the 3 halves. Next argument, which is very crucial. Now we have to pull out some understanding from the theory of extrema. And I'm going to argue the following thing. When you're in equilibrium, you have a real solid. When you have a real solid, the probability to see an energy barrier that is zero is zero. Let's say you're always having some barrier that you have to cross. So, in fact, you can argue that you have a probability distribution for the energy barriers that are of this form. So, the probability to see an x is here, an energy barrier, has to start like x to some eta, and this is a function that simply guarantees that the integral will converge, so it's something that drops down the probability at some large x. So the integral exists and eta is larger than 0. However, we have now the Weibel theorem. And the Weibel theorem says the following. If I have a probability distribution of this form, and I now take n random samples. I take n random samples, and for every sample, I find what is the minimal value. No, out of the n random samples, I find what is the observed minimal value of x. And let's call that minimum value y0. If we do this experiment many, many times, then y0 is going to scale like n to the minus 1 over 1 plus eta. So again, this is a theory for extrema. I have a probability distribution p of x. I'm going to take n random samples from this distribution, and from all the random samples, I'm looking what is the smallest x that I got. I do the same thing with n random samples, I get the smallest thing, and I call that y0, then on the average, that y0 is going to scale like n to the minus 1 over 1 plus 8. Now what happens at the yielding transition? The yielding transition, I argue, is nothing else but the situation where the material changes this property. And from that point on, the probability to see a zero barrier is non-zero. Okay, the system can begin to flow. It becomes fluidized, so to speak. And as I say, in the elastoplastic steady state, the probability to see a zero energy barrier is not zero, meaning that I'm starting here with an eta that is zero. So if I'm starting with an eta that is zero, then put here eta that is zero, then the scaling of the energy barrier changes from 1 over n to some funny exponent to 1 over n. On the other hand, I showed before that delta E goes like gamma p minus gamma to the 3 halves. So gamma p minus gamma to the 3 halves goes like 1 over n. That means that delta gamma goes like n to the minus 3 halves. Goes like n to the minus 2/3. And this is what I showed you before, that the delta sigma goes like n to the minus 2/3, and therefore we now claim that those exponents of third and 2/3 are actually exact, and this is coming from the two obvious reasons. That one, we have a seven-node bifurcation that determines the scaling of delta E with delta gamma, and the other one is through the theory of extrema that says that when you have a yielding transition from a solid to a fluidized thing, where the probability to see a zero energy barrier is becoming non-zero. And this, by the way, is confirmed in numerical simulations. These are not numerical simulations by us, so it cannot be a question for bias. These were Shu simulations, and Shu found that indeed the PDF for delta E changes from a PDF that goes to zero in equilibrium to a PDF that goes to a finite value in the steady state. And we claim this is crucial, and the crucial thing is it really changes the statistics here and is giving us an understanding of these exponents. Okay, let me see what I want to show. You can do all kinds of things with this game. I'm not going to go through all these details. Let me give you an example that you can now begin to do theory. When you understand that the basic thing is the Hessian, you can begin to compute analytically all kinds of things. Here is an example of the result for the shear modulus for an amorphous solid. So there is the Born term, the so-called Born term, which is going to exist only for a crystalline solid, and there is a term here that is only due to the fact that you have the non-affine response, that is to say that is typical to systems that are amorphous and have this kind of plasticity. And what I want to argue to you is that this is a negative definite thing, and this is for us very, very useful, because for years people were asking why a metallic glass has a shear modulus that is 30% smaller than the shear modulus of a crystalline solid, a crystalline metal, the same metal. And now it's obvious why. I mean, you have always a negative definite distributions. We can, of course, compute it for any given system and give an answer for the values of these things, etc. What I want to do in the time that is left is to move a little bit away from the conditions that I've studied so far, which were zero temperature and quasi-static straining, because these are a bit artificial. So let me see, how long do I have? 5. So 5 minutes. Let me jump on the effect of finite temperature. Let me do as an example the effect of finite strain rate. So, effect of finite strain rates. What is going on? What is going to change? You see, when I do it quasi-statically, I'll allow the system at every step to do the non-affine transformation, go back to equilibrium. When I begin to do finite strain rate, there is a competition of timescales. And this competition of timescales is going to change life in a very significant way. So we have established that we have a scaling laws for the energy drops that go like n to the alpha, the sigma drop goes like n to the beta. We now know that alpha is a third and beta is minus 2/3. We have also the energy conservation gave us a scaling relation, but now we should look also at time things. So what is the average time between plastic flow events? Well, if I now have a finite gamma dot, I don't have just delta gamma, then there is a typical time. There is a typical time we're going to call tau plastic, which is the ratio between a delta sigma and a mu gamma dot. Delta sigma over mu is a delta gamma. Delta gamma over gamma dot is just a typical time between the events. And I know all the scaling laws, so I can have a scaling law for this value here. What does it compete with? Of course, the elastic time scale. Elastic time scale, you have now sound speed that takes the effect when you have a plastic change. There is a shock wave that goes through, and it reaches the boundaries of the system in a time that is a typical size of the system over the speed of sound. So now, there's going to be always a system of scale L, which is going to be psi 1, is going to be defined right now, where these two times are the same. Because you see, this object has an n to the beta. Beta is minus 2/3, so it goes down with n. This goes at L, so with system size it goes up. So there's going to be always a crossover between the two, no escape. And you can compute that psi from requiring that this is the same, and this has a scaling of this form. And then when you use this scaling form, you can now look, for example, at what I told you before about the fluctuations of the stress. And you say, aha, now when the system size is sufficiently large or small, I can't remember, I mean sufficiently small, then I'm going to get, sufficiently small, I'm going to get the final exponent that I showed you before, n to the 2 theta, minus 0.8. However, when the system size exceeds the typical size psi 1, I'm going to cross over, I have to cross over to a usual scaling of a intensive variable, is n to the minus 1. And here is the data. So you do this for different n and different strain rates, and you see the scatter, but now you replot according to what this equation proposes, that the sigma squared of n to the 2 theta as a function of L over xi 1, you see that all the data will collapse on one thing, and the slopes here are of course predictable. You can predict the exponents both before and after, and you see that you have a good understanding of the crossover that is going on. Shall we finish with the Herschel-Buckley law, or shall we stop it? Maybe better to stop here. You can do a lot of things with this and understand all kinds of phenomenology, but really what I wanted to drive through is that I believe that we now understand what plasticity is in terms of cell-node bifurcations, the structure of the Herschel matrix, and that all this can be used to understand various scaling laws and phenomenologies. So I'll stop here, and thank you very much for your attention.
Okay, so we have plenty of time for questions.
So in a perfect crystalline solid, the probability of seeing a zero energy barrier event is 0.
Also in an amorphous solid when it's in equilibrium.
Okay. So what you showed is that it's not 0
when you cross the yielding position.
Okay. And then there are consequences of that.
Of course.
And what? So if I understand what Langer, although I don't, must have done is said, how do I make this event non-zero, thinking about it in a crystalline way, by putting in defects, or what?
By assuming that there are these shear transformation zones, then you have to assume, and then you have to assume their density. Then their assumptions multiply. You have to assume they have a density. They have to assume that you have an effective temperature, and you get a theory that is very complex, and I don't think touches the essence of what we see as the plastic events themselves, which are nothing but mechanical instabilities that you can really pinpoint with the use of this simple theory through the Herschel matrix, and showing that eigenvalues are going to 0 in a parallel way, and that this has the consequences. And this is just part of what you can do with this. I mean, there's a lot of phenomenologies that you can begin to understand now.
but you do see things like shear banding in real solid, crystalline solids because of
And
these
also in
defects.
amorphous solids.
Yeah.
Yes.
And by the way, shear bending in amorphous solids is very ill understood. I mean, there's not been a good theory for what is the instability that yields a shear bend in an amorphous solid. It's still an open question. But of course you see those.
Your eigenfunction have another length scale.
The eigenfunction is almost exactly equivalent to the Eshelby solution from way back that studied what happens in an elastic material when you make a small change in a little blob. So this quadrupole form is very typical to a response of an elastic medium to a local change. So you had here a local change, and that tail that you saw is 1 over r cubed.
But they formed kind of rings.
These are maybe the shock waves that are coming through. So when you have the elastic thing, there's now a sound wave that goes out and actually spreads the change in the sigma. And by the way, it may affect other falls. So these big falls that are in delta U that are sub-extensive, that go like n to the third, okay, they are sub-extensive. They're not extensive, but sub-extensive. They are because of an avalanche now. So this shock wave that appears from this local thing can find another guy whose delta is almost 0 and make it fall, and then that one can make a shock wave. So you have these avalanches. This is why you have the sub-extensive scaling. Misha, Uriel.
Well, you
Yeah.
was first.
Okay.
Yeah, I have a strange question to ask you that
Please
is
go.
perhaps not be proper. This wasn't a strange thing, this meeting. Some 40 years ago or so, my now late father-in-law, who was a metallurgist,
Mm-hmm.
and who was involved in all kinds of experiments, particularly with plasticity, of showing me all kinds of things and trying me to understand, challenging me to understand, and I could really not help him very much. Could you say a few words about the history of the subject?
So, in amorphous solids or in crystalline solids?
That's
Because it's very different.
yeah, it's very different.
It's very different. Really, in crystalline solids, the issue. Oh well, let me say the basic mystery is understood. That is to say that you know that plasticity is due to the glide of dislocations. Now, what happens is still
When was that?
in the 80s.
In the 80s, yeah, definitely not.
Not
Yes.
Now, the point is though that when you begin to strain fast or strong, then dislocations multiply. So you start with a few dislocations due to the thermal entropy, you know, what the entropy wants. Then you start to think and they begin to glide, but they also make more and more and more. So eventually, when you have many dislocations, it doesn't look very different from the amorphous solid. And then you are again in the same soup. Okay, so you have to remember this, that also amorphous solids, not everything is understood for the regime where there is a large multiplicity of dislocations. However, where there are a few, it's really doable. Now, for the amorphous solid, I would say that the two people who really carried the subject for, I don't know, 20 years were Ali Argon from MIT and Smappel from Harvard, and both of them were thinking in terms of an extension to the regular solid, to the crystalline solid, in terms of things. And they have a typical energy, and then you have to introduce effective temperature, and all these things. And Jim Langer took this and tried to continue this in a very clever way, I have to say, but in a way that I don't think is really taking the horses, you know, and understanding what is the physics that is going on. So it's a model that tries to explain everything on the basis of a pre-existing little dots or objects or things that I don't know what they are. And I actually started to work on this subject together with Jim, and we are very good friends for many years. And at some point, I asked him, so how do I measure them? How do I measure these shear transformation zones? I said, here, let's make a numerical simulations. How do I find these things? And he said, I don't know. And then at some point I felt that I'm Galilean. If I cannot measure this, it doesn't exist. And I don't think they exist. I don't think that you can actually take a snapshot in any way that you want to analyze it, say, aha, this is the shear transformation zone, the first plastic event is going to appear here. I don't think that you can do this on the basis of a snapshot of the system equilibrium. The plasticity or the event is occurring due to the accumulation of this little non-affine transformation due to the shear.
Let me interrupt you. If you want to watch some of these things using suitable microscopic techniques.
I have microscopic techniques. I
Yeah.
can give you a full picture of the system.
What are the typical distances one has to be able to resolve, and is it?
The particle size.
Yeah.
But I have particles.
Yeah.
I have point particles. And I can give you everything, and give you all the data. I mean, and we looked from all directions. Can I find something special in some points? Since this is something that builds up. It's a process. It's not a structural issue. It's a dynamical issue. It's not a structural issue. So these amorphous solids are structurally homogeneous. And now you make a process. And you see an eigenvalue starts nothing, it's not affected. Then whoop, goes to zero, right? So there's some accumulation of events, process, that makes the instability in some place and not in another place. And these are the eigenfunctions that I can't think about. And it's very interesting to have localization at low energy. Very unusual in the theory of localization. It's a non-equilibrium effect.
Grisha? But you spoke about viscosities, whether viscosity returns into infinity. I agree with you, but as somehow intuitively, well, in the spirit of Deborah numbers, if I take a crystal at a finite temperature, does it also has a finite viscosity on the proper time?
If
like
you have dislocations,
everything flows.
if you have the dislocations.
Yeah, in finite temperature, I always have.
Exactly.
Crystal at finite temperature has a finite viscosity.
Yeah.
So, amorphous solid at finite temperature also must have a finite viscosity.
I agree
What's
with
the
you,
hell?
Grisha. I have no problem with this. But let me just remind you that for years people have fitted these plots
I know.
to Folger-Fulcher things, and they're arguing like crazy whether the infinity is at 600 degrees or 570 degrees. There's no infinity.
So,
Okay, one more question.
Coming back to the eigenvalues you showed, it looked like you had curve crossings.
You may have curve crossing. Let's say, I showed you here an example. The lowest eigenvalue was also the one that went to 0. This is not guaranteed.
But that seemed to cross with the one above.
And generically it will cross. And let me tell you why. When the eigenvalues, in fact, this is something we've understood now. The eigenvalues come in two families. There is a family of the Debye type eigenvalues. Always have long wavelength phenomena, sound waves, things like this, that are always there. These are eigenvalues that don't depend on the strain at all, or very little. You're going to strain, so you can have eigenvalues, and this is now the strain, and they can go, not feeling the strain at all. And there is another family, we call the plastic family, that are sensitive to the strain, and they can, of course, go like this and go to 0. Now, whether there's going to be a crossover here or not, for me, doesn't matter. Let's say maybe this one went like this, and this one did this, or that one crossed over. For me, it's a secondary issue. I just need to know that there is an eigenvalue that eventually is going to become the smallest and become unstable.
Yeah, but each time you cross and you have this avoided crossing, you change the character. Right? So, how relevant is it that it's the lowest eigenvalue? If it comes from, at the end point, it's one of the highest. but then through the interaction it becomes kind of below it.
As I said, all these are extended at the beginning. It only becomes localized towards the end when it comes to heat. And that is always happening when you are the smallest. Okay, so only when it's the smallest eigenvalue you begin to see the localization, that the eigenfunction becomes localized. So it's rich, and as you say, and it can be all kinds of possibilities. In fact, what we now know the density of states of these plastic ones, as well as, of course, the usual Debye ones. So you can do also all kinds of computations for shear modulus, for mechanical properties, because we know how to distinguish the density of states of the two, so you can do analytic calculations that to me are very interesting and get all kinds of predictions.
Okay, I think we had plenty of questions.